many years, the European textile and clothing industries have been the world leaders in terms of innovation, fashion and creativity. Despite increasing global competition and the trend to outsource manufacturing processes to low-wage countries, in 2011 the overall size of TNC industry in the EU 27 represented a turnover of €179 billion and investments of around €5 billion. Despite the strong impact of the global economic recession in 2009, the 146,000 TNC companies still employ over 1.8 million workers, according to the European Apparel and Textile Confederation. The textile value chain is very long and complex, with numerous actors involved in specialized fields: fiber producers and yarn and fabric manufacturers, finishers and producers. It consists of a wide array of companies, ranging from small independent manufacturers to large vertically integrated corporations. Today's textile industry is the fifth largest source of greenhouse gases on Earth, with an overall emission of 3.4 billion tons in 2011. In 2008, the annual global textile production was estimated at 60 billion kilograms of fabric. The evaluated energy and water needed to produce that amount of fabric boggles the mind. 1,074 billion kilowatts per hour of electricity, 132 million tons of standard coal, and 6 to 9 trillion liters of water. For instance, in the production of cotton polyester sportswear fabric, the fiber contributes for 42% to the overall greenhouse gas emissions, whilst finishing and dyeing processes contribute to the remaining 58%, the weaving process being basically negligible. Energy consumption is the most critical issue to be addressed in textile industry. It is estimated that the energy required for the finishing and dyeing processes generates around 3.63 kilograms of equivalent CO2 per square meter. The energy for fiber production generates around 2.82 kilograms of equivalent CO2 per square meter. The dyeing process is one of the key factors in the successful marketing of textile products. In addition to design and attractive colors, the consumer usually looks for some basic products features, such as good stability with respect to lightness, perspiration and washing, both initially and after prolonged use. To ensure these properties, the substances that give color to the fiber must show high affinity, uniform color, resistance to fading, and be economically feasible. Dyeing consists of the aqueous application of color to the textile substrates, mainly using synthetic organic dyes and frequently at elevated temperatures. The dyes and chemical aids such as surfactants, leveling, promoting, or softening agents are applied to the textile to get a uniform depth of color with color fastness properties suitable for the required fabric end used. On the average, the chemicals and primary sources necessary for dyeing 1 kilogram of textile amount to 20 liters of water, 20 to 40 grams of dye stuff, 50 to 140 grams of auxiliaries, and 64 megajoule of energy. Since 69 million tons of fiber were consumed in 2008 worldwide, up to 3 million tons of dye stuffs and 10 million tons of auxiliaries were used in the textile industry. The reactions for the production of dyes are carried out in bomb-shaped reaction vessels with a capacity ranging between 2 and 40 cubic meters and equipped with mechanical agitators, thermometers, pH probes, depending on the nature of operation. Injected vessels are used for the reaction in aqueous solutions, in which heating is effected by direct introduction of steam and cooling by addition of ice or by heat exchangers. Reaction vessels normally span 2 or more floors in a plant to facilitate ease of operation. Solid products are separated from liquid in centrifuges and most frequently in filtered presses. The use of membrane technology with techniques such as reverse osmosis to provide pure solution of dyes is getting more and more prevalent. Dyes produced with solvents and liquids are safer, easier to handle, and save energy costs. However, in some cases, products must be dried. The water content varies from product to product in the range of 20–80%. Where drying is required, air or vacuum ovens, rotary dryers or spray dryers are used. The final stage in dye manufacture is grinding or milling. Dry grinding is usually carried out in impact mills where a considerable amount of dust are generated. According to the life cycle analysis carried out within the BISCOL project, it has been stated that the conventional dyeing production processes are characterized by huge environmental impact on primary sources and greenhouse gas emissions. Within the FP6 European Soffit project, a possibility has been demonstrated to synthesize acid dyestuff with azobones and phenoxazine chromophores through fungal enzymatic coupling, thus opening the way to new safe environmental-friendly routes for biodye synthesis. 2 patents of an anthraquinonic and phenoxazine structure-based biodyes have been submitted, and a bioreactor capable of large-scale synthesis was designed. Starting from these promising results, the BISCOL project has been focused on the scale-up of the process to produce a trichromite for woolen fabric dyeing. Lacases are excellent oxidative enzymes for aromatic compounds substituted by electrodonating groups such as diphenols, polyphenols, and mactosyl substitute phenols. The enzyme also oxidizes orphan paraquinones, aminophenols, aryl diamonds, and polymins. The simple molecules can serve as precursors for enzyme-catalyzed production of azodyes under mild conditions such as room temperature, mild pH, and aqueous solutions. Through the application of this protocol, it becomes possible to produce a wide range of dyestuffs by setting up bioreactors using immobilized lacase enzyme, since it is a prerequisite for using continuous reactors in industrial biotransformations. Through the application of these biosynthetic pathways, primary resources and environment can be effectively preserved. Huge environmental benefits can be achieved by producing biodyes. In general, the combination of biocatalyzed processes with the commercialization of liquid dyestuffs have been demonstrated to significantly reduce the environmental burdens on impact categories most affected by textile industry. The dyeing rate depends on factors such as temperature, liquor ratio, dyeing concentration, and chemicals and auxiliary products and dye path. High dyeing rates bear the danger of uneven dyeing. For this reason, auxiliaries such as surfactant and leveling agents are added to the recipe in order to modify the interaction between the fibers and dyestuffs, to reduce the absorption rates by keeping temperatures high and to improve the solubility of the dyestuff by the presence of salts. The most common auxiliaries used were non-alphenols, but have been banned by the European Union since 2005. The most promising alternatives are oxyethylated amines. The commercial product is mainly oleic-amine, but some more effective and safer products have been produced within the project. An almost 50% lower pollution load has been achieved, and with auxiliary 2 and lower dyeing temperature can be applied to get the same tone. In the context of the BISCOL project, an eco-efficient design of the overall woolen fibers dyeing process has been developed. For removal of contaminations, and because it has to be stabilized in its dimensions, the wool fiber is finished before dyeing. During the pre-treatment, the wool is cored. The washing of wool with non-ionic stand sides is carried out in several successive baths, wherein the wool remains for only a few minutes and at moderate temperature in the same bath. Higher temperatures and mechanical treatment would produce a felt through shrinking and entangling on the segment wool fiber. Therefore, anti-felt treatment with chlorination and polymer finishing is mainly applied. Dyeing processes include bleaching, whitening and dyeing, which is done mainly after scoring. Due to these large amounts of chemicals, water and energy are consumed in different steps of the dyeing process. Within the BISCOL project, two pivotal modifications to conventional production chain have been investigated. First, an anti-fatting wet process has been replaced by dielectric barrier discharge plasma. This is a dry process, thereby reducing consumption of primary resources and the use of polluting chemicals. This kind of process has been selected by the European Apparel and Textile Confederation as one of the flagship for textile manufacturing in the near future. Plasma is a partially ionized gas, composed of highly excited atomic, molecular, ionic and radical species with free electrons and photons. In cold plasma, although the electron temperature can be much higher, the bulk temperature is essentially the ambient one. A plasma can be obtained between electrodes in high frequency and is capable of promoting four processes: cleaning, activation, grafting and deposition. Secondly, the use of eco-design chemicals like biodyes and low environmental impact auxiliaries has been implemented for the dyeing process. Plasma machinery consists of a cylinder covered with a special insulation treatment and 8 electrodes, patented by Next Technology tessili, made of composite material to minimize heat generation during operation. The fabric to be treated is passed around the cylinder, and in the area between the electrodes and the upper surface of the fabric, a cloud of cold plasma and a multitude of random small discharges are generated. As the fabric scrolls under the electrodes, one or more gases are blown, in combination or individually, to promote both the formation of the plasma cloud and different functionalization of the material. In woolen fabric, it's capable of removing the epicuticle layer, the oxidation of the surface, and chemical bond cleavage. By implementing the BISCOL dyeing protocol, a 30% energy saving and 25% water saving can be achieved. Life cycle analysis based on Eco endpoint metrics, i.e. the weighted sum of several impact scores, highlights the remarkable advantages that can be obtained with innovative technologies. The use of eco-friendly chemicals, the replacement of wet processes with dry ones, and enzymatic synthesis of dye stocks allow for reducing the global environmental footprint of the whole process of more than 60%. The calculated ecological footprint, which is the biocapacity that an activity requires to provide the resources it consumes, to absorb the generated CO2 and to simulate the associated waste, shows that the BISCOL process allows reduction of its value by over half of the average. BISCOL 8.48, conventional 19.9.